Hello and good afternoon, everyone. I'm Vina Nasir, the main presenter on behalf of the other two co-authors involved in this research, Professor Ben Hughes and Ms. Azlizawati Ibrahim. So this research title is about SmartTURVENT, Conceptual and Feasibility Studies of Smart Hybrid Windcatcher and Turbine Ventilator for IEQ Enhancement and Wind Energy Harvesting. Currently, I'm a lecturer under the School of Engineering, Faculty of Science and Engineering, New South Wales, UK. So this is a summary of my profile as the presenter of this research. Just an introduction to the key issues of this research. So this research addressed critical concerns about bad indoor air circulation affecting occupants' health. From the recent studies, many emphasize on the challenges involving the need to increase and purify fresh air, and at the same time, is there any chance that we can minimize the energy consumption as well? To counter the issues related to sick building syndrome, we found that more recommendations in both market and research on technologies which need to optimize the use of natural ventilation. Just some examples from the existing solutions. We do have modern wind-driven ventilation system, for example, roof ventilators and wind catchers, which capitalize the rooftop element and also the movement of the outdoor wind. Of course, it's all depending on the design and also the shapes, the forms. These systems induce outdoor air into indoor space, and that will help to enhance the fresh air supplies. At the same time, we also look at the potential for small-scale power harnessing. Based on the turbine ventilators, if you look at the shape of it, it's quite similar to vertical axial wind turbines or vaults, where the blade spins on the vertical shaft. So that's most probably where we can actually harness small amount of energy. Some issues related to the existing solutions are highlighted here. So this research tried to address challenges. For example, the first one, insufficient open air, which hinder the airflow between indoor and outdoor environment. And second one, would like to emphasize on the inadequate source for air circulation, especially in multi-story buildings. And then another issues involving with the compact size and forms of the existing solutions, which also limit the system capacity, especially talking about wind energy harvesting in modern buildings. So to address these issues, hybridizing or a hybrid two or more wind-driven ventilation system is proposed in this research, because we always want to enhance the quality of the indoor environment. We want to increase the ventilation rate, and at the same time, we would like to see if our system could be energy efficient. So our research introduced and aims to evaluate the conceptual feasibility of SmartTURVENT, a hybrid wind-driven ventilation systems of Windcatcher and Turbine ventilator. So the study comprised of 4 objectives, including airflow thermal analysis, assessment of heat-cool recovery performance, power output estimation based on the turbine rotation, and the evaluation of carbon emission savings based on the proposed SmartTURVENT. So if you look at figure 6, it is actually a proposed research framework by us involving conducting thermal airflow simulations, which also require determining the design configuration, creating fluid flow domains, meshing, solver setup, boundary conditions, coefficients, and finally get the solutions. So if you can see under figure 7, the conceptual diagram of this SmartTURVENT. So we propose our SmartTURVENT integrates a wind catcher. So this wind catcher comprises of a vent catcher, which is highlighted here. And also we do have vent turbine, a turbine ventilator, which is put at this part. And these two are separated by a compartment which is created in between. So let's see the design configuration in more detail. So we have a vent catcher, which brings the outside air through these louvers. And we also have vent turbines, which exhaust the air from the inside due to the wind-driven rotation of this blade. So the one that we highlight in green here is the heat and cool recovery unit. We name it as Vent HCR, where we design it located very close by to the incoming air supply unit. So this compact design has the measurement of 1.1 meter times 1.1 meter times 1.1 meters in terms of the length, depth, and height respectively. And it also has the features of 3-blade half-moon Savonius Watts turbine. The diameter of this turbine is about 400 mm and the height is 300 mm. Following the CAD design of the SmartTURVENT, two flow domains were created for the thermal airflow modeling, and the reason why we did not combine these two domains because we wanted to simplify the calculation and would like to reduce the computational effort. So the macro domain, as you can see in figure 9, represent the system with an internal fluid body for the indoor space, and we also have external fluid body for the outdoors. We also create inlet, outlets, symmetry, planes and walls. Everything was set accordingly with certain boundary conditions, as you can see from the previous table. And we also have micro domain, which featured in figure 10, which focus on the outdoor environment, simulating airflow through a SmartTURVENT blade. We created a cylindrical fluid body near the blade so that we can calculate the volumetric average tangential velocity during the rotation. To simplify, the turbine analysis happened in the macroflow domain. So the vent turbine blade was replaced with just a wall. We call it rotation wall, which also allows the setting of angular speed values, and this could be estimated or calculated from the macroflow domain's tangential speed. So if you look at table 2, it also demonstrates the mesh sizing set for both domains. So after the meshing part, then we need to translate and transform all these modules into ANSYS Fluent, and we need to switch on all these models as stated here. So we use transient state pressure based solver, energy model, species transport model, and realizable K epsilon viscosity model for both domains that we had. Time-based modeling was also crucial for us because we need to evaluate and monitor the results based on changes. In the macroflow domain, the energy model was turned off, obviously because the temperature values were unnecessary for this exercise. And then we need to switch on the smooth dynamic mesh method with 6 DOF so that it will enable the rotation of the vent turbine blade, and this will also influence the obtained tangential velocity based on the rotations. So the wind speed that we use is 2 meters per second, 5 meters per second, and 10 meters per second. Why we set this? Because it will mirror the actual urban conditions, and then based on this wind speeds, the critical parameters, for example, turbulent line scale, Reynolds number, turbulent intensity, need to be adjusted accordingly so that we can prevent any calculation errors from the simulation. To address the first objectives, outdoor and indoor conditions were modeled under study 1, as denoted as setting A, B, and C. So setting A represents a minimal temperature variance of 10 degrees Celsius between the outdoor temperature of 20 degrees Celsius and the indoor temperature of 30 degrees Celsius. Setting B, on the other hand, it gives about higher indoor temperature. If you look at here, and the temperature variance is about 15 degrees Celsius, while setting C, it involves very cold outdoor temperature, having the variance of the temperature about 20 degrees. There are 3 operation settings implemented here. So operation 1 activated Windcatchers only without vent turbine blade rotation. Operation 2 allowed vent turbine blade rotation while turning off the Windcatcher louvers. Operation 3 means that Windcatcher and vent turbine will operate simultaneously. So more details about the boundary conditions set for study 1 are shown in table 4. Then to achieve objective 2, we set for study 2, which examine heat and cool recovery unit effectiveness under various wind speeds, involving scenarios where outdoor conditions couldn't provide adequate or insufficient indoor comfort. So wind speed that we use here are actually mirrored those in study 1. And we only switch on operation 3, which means that Windcatcher and vent turbine were operated simultaneously. So we do have 2 settings here. So setting H, it involves heating the vent HER pipes to condition the incoming air for warm, while setting C, it cooled the pipes to condition air for cooling. Other details about the boundary conditions set for study 2 are shown in table 5 here. So let's move to the setting for study 3.1 Roman, which in this study we compared simulated results for optimal indoor comfort, which we target a temperature range should fall between 19 degrees Celsius and 23 degrees Celsius, and the air velocity between 0.1 to 0.25 meter per second, and a relative humidity level of 30 to 50%. In achieving the third and fourth objective of this research, we use MATLAB Simulink to create links, blocks, and subsystems to estimate the final outputs of power harvesting and also carbon emission based on our proposed SmartTURVENT simulation exercise against a condition without incorporating SmartTURVENT. So these were set under study 3.2 Roman and 3.3 Roman. So equation 1 is the energy balance equation which we adopt in this exercise. So then we expanded equation 1 into equation 4 to 9, which accumulate heat losses from a room or space due to occupancy activities, ventilation, building fabric, minus total heat gain from the solar irradiance, internal space heat gain, and also building fabric. So if you look at the equation 2 and 3, they provide the calculation of the power output based on the torque of the rotation of the turbine blade, angular speed, tangential speed, and also the radius of the turbine blade. Equation 10, on the other hand, it estimates the total emitted carbon, which was based on the total power output derived from the model with and without SmartTURVENT, and then we multiply with the carbon emission factor of electricity set in the study. As part of study 3.2 Roman and 3.3 Roman, so we use an actual office room as our on-site data collections within the University compound, University of Hull, during the summertime last year. So we presume that the SmartTURVENT was being operated in 8 hours with almost a constant wind speed was recorded. So as you can see from figure 14, it shows our proposed MATLAB simulated model, which we use to estimate two things. So one is the power output from the SmartTURVENT turbine blade rotation, and another one we estimate the carbon impact of it. So we compared these outputs with and without incorporating a SmartTURVENT system. So the reason why we need to have the on-site data collections was we need to use it as a model validation. So all the information regarding the on-site data collection, including the environmental conditions and measurement device, can be referred to this figure and this table. So our CFD model was run for 15-minute time, validating the before and after a window panel was open. And in order to match our model with the actual test room, particularly at the opening size of the office window, we only set around 36% of lowest opening at the Windcatcher. From the validation, we obtained about 0.4% variance between the simulation results and the measured data, which seems to be acceptable and reasonable at this stage. As referred to our findings based on the microflow domain simulations, we can plot the profile of the tangential velocity and the moment of force for the vent turbine blades, and then we can obtain that, of course, according to various wind speed that we test. Despite that we test with 10 meters per second wind, what we found is that our SmartTURVENT's angular speed in RPM was insufficient as compared to the RPM that we could obtain from the existing turbine roof ventilators, highlighting the need for the improvement of the turbine blade. So now we move to the analysis findings on the study 1, begin with the setting A. So from this figure, what we can conclude that obviously higher performance in all SmartTURVENT operations can be observed because of the increased wind speed. But the most interesting ones, we can observe that the hybrid operation of Windcatcher and vent turbine under operation 3 could accelerate the heat exchange between indoor and outdoor in a shorter period as compared to single operations like operation 1 and 2. So from the simulation with the setting A, hybrid operations achieve an indoor comfort within 15-minute time with 5 meters per second and 10 meters per second wind speed. Now to setting B in figure 19, where the indoor temperature was set higher than setting A. So what we can observe from this is the hybrid operation under operation 3 managed to achieve less than 5-minute time with 5 meters per second wind speed, while the single operations of operation 1 and 2 took more than 15 minutes minutes time just to sit within a comfort range. So under this setting B, as what we can observe as well is the hybrid operation could prolong the comfort condition of the room until 20-minute time, which gave us an interesting finding as well here. So for the setting C under this figure, so where the outdoor temperature was set lower and colder than setting A and B, what we can observe, despite with low wind speed setting for 2 meters per second, but because of the cold wind from the outside, the indoor temperature was found reduced, reaching a comfort range within 15-minute time. Obviously, with higher speed, cold wind, it speeds up the indoor temperature reductions. For example, under 10 meters per second wind speed, the time took to achieve a comfort condition was about 3 minutes. But of course, the comfort condition could not prolong more than 4 minutes because of like very, very cold air. To sum up what we found from figure 18 to 20, so this is the 20-minute plot of indoor temperature versus reduction value comparing operation 1, 2, and 3. So from this plot, what we can observe is that the hybrid operation of Windcatcher and Turbine demonstrate the most optimum solution in speeding up the air movement and heat exchange between indoor and outdoor environment in achieving indoor comfort. However, in some particular setting, the comfort environment could not be prolonged. Therefore, to ensure that hybrid operation to be more feasible, we believe that smart control unit, which connects the environmental sensors and dampers, will need to be considered as part of the SmartTURVENT design in future. Then we will move to the heat recovery components under study 2. Now we move to the main findings for study 2, and from this figure, what we found, there is a good correlation between Windcatcher, Turbine, and HCR. And when we set with higher recovery settings, the system could enhance the indoor temperature change even more. The findings also showed us that the higher wind speeds induce more air into the systems, and that could rapidly change the indoor ambient temperature. For example, under setting C, when we set the wind speed of 10 meters per second, there was a quick rise from 15 degrees Celsius to 18.6 degrees Celsius occurs after 60 seconds, and the room temperature reached about 20.6 degrees Celsius after 7 minutes. Another interesting finding is when we lower the wind speed to 2 meters per second, setting H using 90 degrees Celsius pipe could prolong the temperature, even increase it up to 20 minutes, whereas 60 degrees Celsius and 30 degrees Celsius pipes require more time to recover and to supply the comfort temperature. At 5 meter per second wind speed, setting H with 90 degrees Celsius pipes extended the increase up to 12 minutes before gradual decrease. Now we move to cool recovery. So setting C with low wind speed, of course, require more time for comfort conditions, while when we set the setting C with negative 5 degrees Celsius pipes, the system could reduce the temperature rapidly when set with high wind speed. These are the main findings under study 3.1 Roman. So in this figure 23, you could see the 20-minute plot of volumetric indoor air velocity and of relative humidity comparing different SmartTURVENT operations. So under 2 meters per second outdoor wind speed, what we found is that the room could achieve a comfort air speed after 10 minutes, while when we set with higher speeds, which 5 meters per second and 10 meters per second, they cause discomfort later on and could not prolong the comfort speed as required. We also found hybrid Windcatcher and Turbine operations effectively regulate indoor humidity levels as compared to single operations. However, the study also emphasized the importance of us to optimize the wind speed so that we can prolong the comfort conditions on both air velocity and humidity. So in our future research, we also need to focus on controlling air movement within acceptable range, and we need to improve the zones related to the wind catchment, exhaust air, and heat recovery. So now let's move to the main findings for study 3.2 Roman and 3.3 Roman. So from the simulated conceptual analysis, what we found is that the proposed SmartTURVENT system could produce about 0.4 watts, 11.3 watts, and 69 watts, which could be harvested from the wind speed of 2 meters per second, 5 meters per second, and 10 meters per second, respectively. So with these power output, we obtain the carbon emission values, and we compared the scenario incorporating the SmartTURVENT versus the one without incorporating SmartTURVENT. So from the MATLAB simulating model, our SmartTURVENT system managed to reduce the carbon emission from the energy operation system up to 47%, with an average carbon saving about 13%. However, the increased energy loads here could drastically minimize the carbon saving performance, on average about 67%. Because of this, we believe that controlling the system will help us optimize the energy and also carbon saving, and this is what we need to do next. So to conclude, what we found that our SmartTURVENT featuring a hybrid Windcatcher and Turbine ventilator holds quite significant potential for future heat cool ventilation in buildings. It has a compact design with separated wind catchment and exhaust zone, and make it quite practical for small scale structures, for example, residential homes and shop lots. So the hybrid operation accelerates heat exchange, which our proposed system achieve about 6 to 40% and 11 to 55% faster temperature adjustment than single operations, operation 1 and 2, with an average energy and carbon saving about 13%. So for our future work, what we believe that there are two things that we need to focus on. First one is to involve tuning the turbine blade so that we can get higher power output. And then we need to integrate smart control system with sensors so that we can obtain precise air intake and exhaust control. Just a small acknowledgement. This work has been supported by the Faculty of Science and Engineering, New South Wales, under the 2022-2023 Research and Impact Staff Fund of £3,845, which was awarded to me last year. This is just a list of reference of the previous related works to support our research. So now we reach the end of the presentation. Thank you very much for your attention. And now I open to all audience for any queries to the research work. For the clarification, network, and intended collaboration, you know that I can be contacted through my emails like stated here. Thank you.